Alright everyone, welcome back. This is our very last module. So this is module number 4, where we're going to be talking about time series. So this is going to be a brief introduction. Well, not a brief, it's going to be a class or change of an introduction to time series. Alright, so suppose we have 5 years of monthly subscription revenue. We need to uncover the true trend, adjust for seasonality, and forecast next year's revenue to guide marketing budgets. So that would be kind of our goal walking into this. So at the end of this lesson, what we would like to be able to achieve is the following. First, we want to define what stationary is and interpret the ACF plot. This is going to help us not only predict but understand what's happening inside of our time series. We then want to be able to smooth noisy data via a moving average or exponential methods, and we'll talk about the difference between those two. We want to be able to decompose a time series into its components. So if you remember back from Stat 2601 when you were first introduced to this, there was 4 main components. We're only going to be breaking them down into the 3 components because 2 are going to be merged into one. Once we're able to do all of this, then we want to be able to do that prediction into the future. So we want to generate forecasts. So we're going to look at a naive method, a moving average method, and a Holt-Winters method. And then last but not least, well, if we have these different ways of being able to predict into the future, and we potentially had a way of being able to determine how true we were to the actual outcome of this, we could evaluate the forecasting accuracy. And we have 2 methods of being able to do that. We have the mean squares error or the root mean squared error calculations that we're going to be looking at. All right, so let's jump into this. All right, so a first step in data analysis is understanding the data. So in Stat 2601, now this wasn't, if you've done the 2507 or some variant of that, you might not have seen time series. If you haven't, not a problem. We are starting right at the very beginning. So you can kind of scrap everything that you've done in 2601 up to this point in time and think of this as we're starting fresh. But if you did take the Stat 2601, we did discuss that there were cycles, there was trends, and there was wandering and a seasonal component or a combination of all of these that basically built up our time series. So we decomposed our time series, or we thought of this as there's a trend, there's an upgoing or downgoing, or maybe it's just staying completely flat over the duration of time that we are examining this. There could be a seasonal component to it. So is it around Christmas time? Sales always increase or decrease? Does this happen every single year? A cyclic component. So again, kind of like a repeated pattern, but it's not yearly. This could be following a standard business cycle. So this can go 2-3 years. And then the next repetition may not be in exactly the same sort of way. So it becomes very difficult for us to be able to model, which is kind of why we've removed that aspect and we've associated that with trend in this case. And the last little bit, that random wandering, that noise that we have from the data. All of these things make up our time series. So out of those 4, we're going to break it down into the 3 main components. All right, so in this lesson, we will discuss methods designed specifically for enhancing the understanding of the data. So these methods include smoothing methods for smoothing out anomalies that obscure the big picture. So given a time series that contains seasonal and trending behavior, it may be that the repetitive seasonal behavior is covering up some important trending moments in the data that can be seen better after that seasonal effect has in fact been removed. Think of it as, if we have a seasonal component, we always know that at certain point in times we're going to see a boost in things. It's really hard to compare, month to month, quarter to quarter, year to year when these not anomalies, but we know that they're going to be there. They're increase or decrease in total revenue. It's hard to see, what is actually happening overall. How do we compare months to months without these massive amount of increases? So if we were to say change a price or something along those lines, or a different model, something, we're changing something up, we want to be able to evaluate that in using some standard metric. All right, so before we smooth or we forecast, we must ask the question, is our data behaving consistently over time? So that's really what the question of stationary is going to be able to answer for us. So can we trust, this is a good thing, can we trust last December subscription prices or subscription revenue? Does this hint at, this coming December? Are we able to kind of predict these sort of patterns in there? Okay, so when forecasting next year's subscription revenue, our confidence hinges on whether past patterns persist. So is the overall trend still happening in exactly the same way? So stationarity and autocorrelation, let us test that assumption. And we're going to be talking about this more in greater detail in the next lesson. Here we're just going to do a brief introduction to this. So for a time series to be stationary, and there's two different types, there's weak and there's strong. We're not going to be focusing on strong stationary because it's well beyond the scope of the course and it's not really used all that much. But weak stationary, well, that's a little bit easier to deal with. So weak stationary, there's really three main components, but if you have the two, you have the third automatically. So it has to have constant mean. What that means is the average can't change over time. All of these can't be dependent on time. So if I'm looking at a span of time, at one point I can't have a higher average than what I would have at another point in time. It needs to be consistent. Autocovariance. Now I'm going to define this more specifically next time around. If we have this, we have the constant variance. The autocovariance, we'll talk about that in the next second or the next slide here. We're just talking about different points in time. So if I say I want to go from now to 1 month into 1 year into the future, so December of this year to December of next year, and I want to see, well, if I'm a year apart and I'm looking at that time series, and again, I will explain more of this when we get to that point in time, but how are the data points related to one another when we look at that year apart? So why does this matter? So two things that we can get from this. It ensures that our smoothing and forecasting methods aren't chasing kind of like shifting averages. So what do I mean by this? I mean that, let's say if revenue has an upward trend, so it's increasing. A 12-month moving average, when we get to that point and explain exactly what we're going to be talking about this, is going to lag behind in true growth. So if something is growing quickly, if I'm taking this moving average, it's not going to be able to capture that in an appropriate amount of time. So your forecast for next month will be lower than actual, causing you to potentially under allocate inventory or marketing spent. But it also could be in the other way around. If there's a downward trend in the sales, you might overestimate your future revenue, overstock, or even overspend. So you want to be careful about these things. If revenue drifts upwards or volatility changes, what we're going to be talking about first is naive forecasting. This will mislead budgets and inventory. So when variance increases over time, kind of like from a stable launch to a volatile growth phase, think of it like that. A fixed window smoother or a parameter model would underestimate the true uncertainty of all of this. So the confidence interval would become too narrow, exposing you to unexpected, say, demand swings. So being able to predict into the future, again, if we have something that is not stationary, it becomes very difficult for our models to be able to interpret this. So a stationary revenue process means last quarter's average and variability are good guides for the next quarter's planning. So having a model that's stationary, again, helps us to be able to predict into the future. Now, what about autocorrelation? So autocorrelation measures how similar time series are to itself, just as I said, different points in time. So this is what's referred to as lag. So lag in the parameter K is how far away are you in this time series. So think of it as I'm looking at when I'm trying to compare autocorrelation. Autocorrelation just means I'm talking about the correlation between something in itself, just at different points in time. So remember when we were doing correlation beforehand, and I have my data points, my X's and my Y's. So what I would do is I would take my xi value, my yi value, pair these together on a scatter plot and say, okay, let's graph this. Let's see this scatter plot. How linear is the relationship? So the correlation, the closer it is to a positive 1, again, we have that strong positive linear relationship. If it's negative 1, it's a negative linear relationship. If it's 0, there's no relationship whatsoever. So that was when we had x and y points, and we wanted to know, well, how related are these two things together? Now what we're talking about is the relation between something and itself just at different points in time. So what I'm doing is I'm creating new ordered pairs, and I'm saying, let's just call this time series yi. So I'm looking at yi, and I'm looking at yi plus. Now I'm going to go k steps into the future. So this might be a year into the future. And I would say, okay, what is the relationship between a point and itself a year into the future? And I would go across all of my points of this. So starting at, say, month 1, a year into the future, month 2, a year into the future, month 3, a year into the future, until I can't go a year into the future anymore. And I built this set of points. I graph it in the same way with the scatter plot. So I'm graphing all of these and I say, well, what is the relationship with this? And again, if it's positive 1, it's a strong linear, negative 1, same idea. But what this is telling us is what is the relationship between a point and itself a year into the future. So if I want to be able to predict what's happening a year into this future, this strong relationship is really going to be able to help us. So a lag of 1 means we're looking at, say, this month and last month. Lag of 12, as I said, it's this month and a year from now. So at each lag, basically what we're doing is the following. As I said, we're going to pair up each of this y sub t. We can go minus t or we can go plus t. It doesn't really matter. We're just going that difference in points in time. So we're pairing these things together exactly as I have here. We calculate their correlation, that linear association across all such pairs. And what we're doing is we're calculating this rho sub k. That is our correlation. So this is, again, between negative 1 and positive 1. 0 being there is no relation between these things. So imagine you want to know how much, say, this month's revenue echoes past revenues. So again, autocorrelation answers exactly this. How well the series predicts itself at fixed time shifts. This is our lag, fixed time shifts, and that fixed is in fact k. Now, before I go through an example of this and how we use the autocorrelation function, or ACF function inside of R to be able to graph this for us, we want to be able to understand this a little bit better. So again, why does it matter? First and foremost, if there is a trend, what should we expect to see if there is a trend in this? So a trend usually means that, you know, we're either going upwards or downwards in terms of the data. So if we're going upwards or downwards, think of this as there's a lot of past information that needs to be taken into consideration for future. So there's going to be, you know, if I'm increasing here, then I'm still going to be increasing here. If I'm decreasing here, I'm still going to be decreasing here. So the relationship at these different lags, this information that's kind of being passed along, will still remain relatively high. So when we're looking at that autocorrelation function at different lags, we're going to see a slow decrease or decay in that rho sub k. So when two things are strongly related early on, but then the farther we get, the less of that relation it's going to be. Again, we're going to see that rho sub k shrink over periods of time. So when we graph this, what we're going to be doing is graphing the correlation, which is going to be on my y. My x is going to be at my different lags. So what I'm going to see is a slow decay downwards. And what this applies is a long memory process. The seasonality aspect, well, what can we expect to see? Well, we could look at different spikes along the way. So if we have, say, a yearly cycle, so we know that we always have sales during the Christmas period or the December period, then we should see at lag 12, at lag 24, spikes that are happening. And maybe at the first year, we're going to see a bigger spike. Maybe at the second year, a little bit of a smaller spike because we're getting farther away. So what happened 2 years ago might not be as important as to what's happening 1 year ago. So the strength of that correlation might diminish over periods of time, but we should still see those little kind of bumps along the way. And this would imply a yearly cycle. And it doesn't need to be a yearly cycle. It could be a monthly cycle. It could be a quarterly cycle. It really depends on what we're looking to model. And what else is this ACF going to do? It's going to help inform our choice of smoothing window and seasonal period. So this is going to also help us when we are looking to smooth out the data. What type of, or what, I'm trying to think of the right word here. Well, we'll get to that when we get to that. What period of smoother we're going to be dealing with, and we'll show you examples of why this is important. So interpreting the rho sub k here, that's exactly what I have here. That's my rho, that's my correlation at lag k. High positive means strong similarity, so seasonal repeated patterns. Near zero, no linear relationship at that shift. And negative and inverse of this. So what we saw could have been an increase, now is going to be a decrease. All right, so what we're going to do now is we are going to simulate some data. This is going to be kind of our exercise number one. Going to build a time series that I'm forcing there to be a trend and a seasonality in there, and we want to be able to just kind of quickly look at the ACF function that was inside of R and kind of get an idea of what we are in fact looking at, where potentially these things might help us in terms of a smoother. Okay, so let me jump over to R. Here we go. So I need two packages. If you haven't installed them yet, this is on line 1 and 3. So just uncomment that out. It's the install.packages tswge and install packages forecast. I believe I already have these installed in here, so I just need to load them from the library. So for me, I'm just running line 2 and line 4. There we go. All right, so the first thing I want to do is I want to generate data that is going to make up my time series here. So since I'm randomly generating data, I do want to set the seed. So my seed will be set to 42. I'm going to generate 60 data points. So n is going to 60. Now I'm going to build a time vector, which is just going to be a sequence of going from 1 all the way up to n, so 1 to 60. Now I'm going to build the trend. So the trend, think of this as, I'm going to use my screen up here. I'm adding a line to this, or something with an intercept in a slope. So for me, what I'm doing here is I'm saying my trend is equal to 100. So this would be my intercept plus 2 times time. So it's time marker 1, time marker 2, all the way up to time marker 60. I'm just taking 2 times that, adding it to 100, and this is going to build my trend. So we see from this that the slope is 2, it's positive, it's increasing, and the intercept is at 100. So I build my time, which again I am doing on line 12 here. Now my seasonal component on this, I'm going to use the sine function. So using 2 pi times time in my numerator, my denominator, I'm dividing it by 12. So I want it to repeat itself every 12 cycles. So this is going to be key. So this will be, well, we'll see when we graph this up here. This is going to be things that happen at the, say this month, and then a year from now or a year previous, that relationship should be strong. And I'm going to add some noise into this now. So it's going to follow a normal distribution with a mean of 0 and a standard deviation of 5. And now I'm going to build my time series, which I'm adding these 3 components to it. So I'm going to call this as sales. Sales is going to be defined by trend, season, and noise. Now I can build it into a time series using the TS function. So it includes the vector. This is my time series that we just made up. Starting point, let's say it's going to start in 2019. 1 based upon the frequency. The frequency is 12, so this is every month. So this is the first month of 2019 is when my data starts. Now notice if I do TS underscore sales, I don't have this in here, but if I wrote this down, look at how the data is already presented to us. So it knows it has a frequency of 12, so it's based upon every single month, starting in the year 2019. So I've got January 2019, and I've got my first point inside of here. So remember, again, this is just the trend, the seasonal component, and the noise that is added on. So 118 and change, 118 and change for February, so on and so forth. And yeah, this is my time series. Okay, so let's go down here. So if I wanted to plot this using I wanted the autocorrelation plot, I'm going to use the ACF function. So I'm going to put in TS underscore sales. That is the time series that was just created for us, or that we just created, I should say. And I want to label the main title here, and I'm going to say ACF monthly subscription revenue. All right, and we see the graph of this now. Let's just explain the graph here for a quick second. So this first line here, this represents a lag of 0. So this is comparing a time period to itself. So the first month, first period, the first whatever, comparing it to itself. So think of this as, instead of when I was doing, if I have an X and a Y and I'm grouping these things together, so an X sub I, Y sub I, and I'm asking what's the correlation of this. Suppose these are both Y sub I, so this is Y sub I, Y sub I. I'm grouping things together and I'm asking what is the relationship between something and itself. It's always going to be 1. So the ACF at 0 lag is always going to be 1, and that's exactly what we see here in our graph. At lag 0, that correlation, that rho, is in fact 1. Now from that, I'm going to go one step ahead. So I'm saying, what's right, or what's the relationship between right now and a month from now? Well, it's a strong correlation. So that means that information that is more or less being passed along the way. So how strong do I want to associate what's happening now with what happened in the last month? Well, in terms of this, it shows that the relationship is fairly strong. Not as strong as it currently would be with lag of 0, but again, that's always going to be the highest. But it is pretty close to 1, so that's a strong linear relationship. So again, if I'm looking at a point now and a month from now, and I'm doing this over the entire period of time, this has a strong positive relationship. So as one increases, the other increases. But as we see as we go farther down, so this would be 1 month in, 2 months in, it's not as strong. There's still a positive relationship, but it's shrinking. So the farther we get away from that very first month, the less of information is kind of like being passed along, more or less. So what we can use now to try to predict that much into the future, well, there's not as strong of a relationship between things. But notice there is a dip here, and then we see a slight bump that happens around year number 1, which is, again, that repetition that comes into play. So we set it, the seasonality, to have a sine function, so that is our normal up and down sort of wave. It's going to repeat 12 times overall, so it is showing a little bit of a relationship of what's happening here every single month. What else do we have here? Yeah, so we see a decrease, so we know that a trend is in fact happening, and we do see these little spikes. So again, what we are seeing is that seasonal pattern that's also associated in there. Now there are the blue lines in here. Think of this as a confidence interval. So like the hypothesis test would be, is rho sub k equal to 0 versus it's not equal to 0. So if anything falls in between these blue lines, we can basically assume that, okay, whatever noise is happening there, it's just noise, and the true value is going to be 0. So once we hit year 1, we're at month 1, 2, 3, 4, 5 around here, like these ones here, we basically consider them 0. Anything above or below would consider to be statistically significant. All right. Switch my screens, get back here for a second. All right, so what we want to talk about now, and the first part, before we get into the forecasting, is the smoothing of the data. So what the smoothing is going to do is it's going to help us understand the trend of the data. So if this is done correctly, we should be able to minimize the day-to-day or the month-to-month or the quarter-to-quarter, year-to-year fluctuations that would be happening inside of our data. So the data has to have a seasonal component to begin with, to be able to, it doesn't have to, but it is more useful, I should say, when there is that seasonal component, being able to remove that. All right. So several methods exist for smoothing out the noisy, possibly unimportant behavior from a time series. So it's important to understand basically the original signal in there, the trend of what's happening is better understood. So we can again be able to compare apples to apples. And I say that because, you know, if I want to be able to say whether or not a price increase has affected the demand of a product, well, again, if I know sales are naturally going up or it's going down during a period of time, that's going to inflate what's happening there. It's not going to allow me to see what's actually happening overall. So being able to smooth out these day-to-day fluctuations or potentially remove the seasonal aspect of it is beneficial to us. All right, so the first thing that we're going to be looking at is a centered moving average smoother. So this method is for replacing data values in a time series with an average of data values surrounding and including that data point. So basically I have my original time series. I'm looking to create a brand new time series. This time series, again, we're going to be averaging out these fluctuations. And it's all going to depend on the order of the time series that we are in fact dealing with. And this is kind of where that ACF graph comes into play. If we know that fluctuations are happening at very specific times or can guess those specific times, we can average those out. So for example, we'll start with a order 3 smoother. So an order 3 centered moving average smoother has a formula that looks like this. So remember, we are starting with a time series. We'll call that time series X, and we're going to build now a time series S. So at X sub t, we create a new data point. If possible, we create a new data point S sub t. For order 3, this is what we're doing. And basically the name says it all here. It's a centered moving average smoother. So the centered part means when I'm calculating S sub t, I'm going to look at the true values, X sub t, but very specific ones. So S sub t is what I want. The center of that is going to be X sub t. So this is in order 3. So if I remove the center, I'm now looking at 2 more observations. I want to go equal parts on my left and my right. So I'm going to go 1 to the left. So I'm going to look at t minus 1. I'm going to go 1 to the right, t plus 1. So I'm taking those 3 points and I'm just dividing by 3. That's it. Simple moving average. So as x shifts, or sorry, as S sub t shifts, I'm going to shift all of my x's as well. Now I said sometimes we cannot do this, or not for all data points. It's because, again, for an order 3, I'm grabbing a point to my left and I'm grabbing a point to my right. So let's suppose I have values x1, x2, x3, x4. I want to create an S1. So creating an S1 means x1 is going to be my centered data point, and I have to be able to go 1 to the left, 1 to the right. But I don't have anything to the left. There is no x sub 0. So I can't actually calculate S sub 1. But what about S sub 2? S sub 2 requires me to go x sub 2, 1 to the left, 1 to the right. Well, I've got those. I've got x sub 1, x sub 3. I can add those up, divide by 3. Perfect. I have S sub 2. S sub 3, same idea. The center position, x3. 1 to the left, 1 to the right, x sub 2. X sub 4. I take those 3 data points, divide by 3, done. S4, hopefully you already have the idea here. If I go here, again, 1 to the left, perfect. X sub 3, 1 to the right. There's no X sub 5. I can't calculate this one. So I've created a new time series. In this case, it's just going to have the 2 data points, but my 4 original ones, I have 2 now. This would smooth out order 3, those types of fluctuations. So smoothing helps to identify in kind of looking at long-term trends in data by removing short-term fluctuations, as we said. Again, it's the key parts here. It's particularly useful for understanding the overall direction, so the up and down direction of the time series. Where is it moving to? And it may not be moving at all. It might not be going up or down. It just might be staying flat, stationary, or in terms of the constant average. There we go. What else we have here? So there's really 2 cases for the centered moving average smoother. The odd case is the easiest because if I'm talking about an odd number, well, my center point is my starting point. So if I'm doing an order 5, that my first point is there. 1 point removed from an odd number gives me an even number. So from 5 I go to 4. I can divide that by 2. So that's 2 to my left, 2 to my right. Easy as that. And that's all we're doing for the odd cases. I take that centered moving or centered part. That's my first point. And then I divide the even parts, or what's remaining, by 2. Half on one side, half on the other side. Perfect. When it's even, it's a little bit more annoying, but not a huge amount. All right, so let's say an easy example here would be in order 4. So let's go, I have x1, x2, x3, x4, x5. I want to do in order 4. So don't focus too much on the formula here. This is a little bit more annoying than anything else, but this is what we're doing. So let's say I was looking to calculate S sub 3. So for S sub 3, again, that's my first point. Okay, this is in order 4, so I'm looking at 4 points. That's exactly what the order refers to. How many points are we averaging out here? Here I'm doing 4 points. So if I take one of those points away, I now have 3 points. Okay, I can't divide 3 evenly. But what I can do is I can take 1 point to my left, 1 point to my right. Okay, so now I have 3. 3 out of the 4. But what do I do now? Do I take x1 or do I take x5? We're going to cheat a bit. I'm going to take half of each. So I'm going to take half of x1, half of x2. Now I have my 4 points in total. I have my center, which is x3. I have my 1 to my left and 1 to my right, so x2, x4. And for my last point, I'm taking half of x1 and half of x5. So if I add all of those up and then divide by 4, so all these up, divide by 4, that gets me S3. And that's exactly what this formula does. So it looks at all of the kind of those center whole points, and then I'm grabbing half of my farthest left one and half of my farthest right one. That's it, that's all. That's where the 2m comes from. So I can factor out, I can rewrite this as 1/2 x t minus k over m, which looks a little bit more fitting with what we kind of have here for this middle part, this 1 over m. That's exactly what we're doing, except I'm just multiplying it by half because I only want half of the information from there. Now, we don't have to do these calculations by hand. This is all going to be done in R4s, but I just wanted you to understand what's exactly happening here. And of course, we have 2 examples here. So again, for that order 5 center moving average, again, it's odd, so it's an easy one to be able to do. I have my center part, which gives me 1 of my points. I need 5 points in total. So now I have 4 remaining, 2 to the left, 2 to the right. Here's my 2 to my left, 2 to my right. This should be -1. There we go. As we said, the 4th order, a little bit more of the pain because it's even. But again, same idea, exactly the same calculation we had beforehand. I could write these as over 4, this as over 4, and then just multiply this by a half here, and multiply this by, say, a half here, if that's easier to understand. But that's it. So I'm grabbing the 3 main centered points, and then I'm grabbing half on my ends. All right, so the centered moving average smoother has 2 basic units. Uses. I think I might have said units. That's not correct. Uses. So smoothing designed to remove potentially meaningless fluctuations from the data. So it could be important, could not be important. It's removing cyclic behavior from seasonal or other cyclic data with fixed cycle lengths. Now, what we're going to be using is we're going to use the TSWGE package, and the function specifically that we're going to be calling is ma.smooth.wge. So we're going to be looking at this one. So for exercise 2, what we're going to do is we are going to build a time series, and we're going to be looking to perform an order 5 and an order 10 smoother, and we're going to say, well, what do we notice about this? Now, obviously, I already have kind of that information in here, so pretend we're not reading the 2 notes just yet, but we'll get to those 2 notes in a sec. But if we get back to R here, so for exercise 2, I'm building a new time series. So again, I'm going to set a different seed here this time. So this seed is 6,946. I'm building a time vector t going from 1 to 60. This time around for my seasonality, I'm going to use a cosine function. It doesn't matter, sine, cosine function. So 2 pi t divided by 10. So I want this to repeat itself every 10 periods. And my trend line, it's going to have an intercept of -2, a slope of 0.05, so it's still positive, still increasing. and then multiply that by time. So let's plot the individual aspects of this. So first, let's look at the seasonal aspect. So this is just my cosine function. So starting at time is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now look at the 11th position. So from 1 plus 10 gives me my 11. I'm starting off exactly the same way. And if I go down here, where am I? Again, 10 steps into the future. Well, I'm exactly here. Here I'm exactly here. Here I'm exactly here. So this is repeating itself every 10 cycles in exactly the same way. So this is typically would not happen in a seasonal behavior, because there's going to be some seasons, like if we're looking at things that have a very heavy holiday traffic. So if we're looking at Christmas time and travel, we might see in December big spikes, and those big spikes are not going to happen to the same degree every single year. Some years might be heavier in travel than others, but we would still expect to see a jump at those points in time. Here, what we've just created is artificial, but it's showing exactly what we need to be able to show that at these points in time, this is the repeating behavior, and it repeats perfectly every 10 periods. In terms of my line, so my underlining behavior of my time series, I want it to look like this, so increasing. And if I put these two things together, this is what my data would look like. So I see an increasing pattern, but I have this seasonal effect to it. All right. So now let's create some random noise. This is what we're normally going to get when we get the data. There is going to be a noise aspect to it. So I'm going to use a normal distribution. Standard normal distribution, n is equal to 60. So again, I'm generating 60 data points of random noise. I want to add this to my x here. So I'm saying x is going to be my new time series, and it's going to be made up of that cosine, so that's seasonality, the trend, and the random noise. So if I plot x, this is typically how we would get time series data. Okay, looks like a little bit of a mess, kind of all over the place here. But that's the thing, I want to be able to smooth this out. I want to be able to smooth those fluctuations out. We know what the underlying theme should be. We know what the seasonal pattern is. We know exactly that it repeats itself every 10 cycles, and we know that it has a positive trend. So let's see if we can figure that out. So what we're doing first is I'm going to do a moving average smoother of order 5. So it's going to group 5 monthly chunks together and take the average of that where it can, because again, if I'm starting at a specific, I need to be able to go 2 to the left, 2 to the right. So I'm not going to be able to do the first 2 months, but I'm going to be able to do a good majority of this. So if I run this ma.smooth.wge, there's 3 inputs. The first one, x, is my time series. The next is going to be the order, and whether or not I want it to be plot, I'm just going to set these equal to true. So what we see here are 2 different shades of line. So I have a thinner black line here, or kind of grayish line. This is my original time series. I have a thicker black line. This is my smooth data. So what do we see from the smooth data? Well, we still see fluctuations that are happening here. And we do see that it is in fact increasing. So the question becomes, can we do better than this? Well, yeah, we can do better if we know what that repetition is going to be. If we know that it repeats itself every 10 cycles, we might be able to do something with this. So let's look at this for a second here. Let's do an order 10 smoother. Now notice that solid black line right in the middle here still has some fluctuations going on, but it's a lot smoother. Let's change this up for a second. Let's go back to when I created this time series on line 35 and added on that plus J or Z, that random component. Let's say I got rid of that random component and just left it as the cosine and trend line in there. So again, plotting this is the data that we have. If I were to do an order 10 smoother, what would the data look like now? Well, I no longer have those up and down fluctuations. I have a perfectly straight line. Excellent. So why wasn't it perfectly straight the last time? It's that noise component. That noise component is always going to be there. So the closer I'm getting to a straight line, the better off I am. Now, if I did, say, in order 20, Notice it's still the perfect line inside of there, but I've lost information along the way. So I don't want to say I kind of guessed that it was 20, but it's just a multiple of the original, which is 10. Um, I'm losing out on too much. I'm smoothing too much away. So I really want to get as close to the true as possible. I'm not always going to know what that is, but I'm going to try and get there as much as possible. So with an order 10, I get that. All right, let's go back. Let's do plus Z inside of here. Oops. Run. But let's use that ACF function for a second. ACF, and I want to do this on X. So what do we have? We have lag of 0, again, correlation of 1. Then I have a decrease because I'm down just above a 0.5-ish here. But we see a decrease. Okay, now we're in a range. So I've got 1, 2, 3, 4, 5. So 5 months in, 6, 7, 8, 9, 10. What we're starting to see again is these peaks that are happening here. Yet there is the noise aspect to this, but I'm seeing a decrease. Seeing a decrease in rho, which means that there is a trend component to this. But I'm seeing this up and down sort of pattern, and it looks like it's plateauing, or not plateauing, but it looks like it's changing from up to down somewhere in this 5 sort of, or 10 sort of area. So it kind of looks more like it's happening at 9, but we know the true value is actually 10. But because of the noise, it could be a little bit confusing. Let's see if I actually remove this. Do I get a better one? There we go. So if I remove the noise from this, look exactly what happened. At 10, I get that peak, and that's exactly what I'm expecting to see. That means there's a strong correlation between what happened at time 0 all the way up to time 10. So if I go 10 months into the future, that strong relationship is telling me that if I want to be able to predict 10 months into the future, well, this is giving me positive outlooks on that. Or yeah, if I want to predict what's going to happen next month, well, all I have to do is look 10 months previous, and that should give me a good rationale as to what's happening here. So a little bit of noise kind of throws things off. That's kind of what was just showed here. So adding that plus Z in the ACF, but the ACF kind of gives us a general idea of what of the order that we need. So it'll tell us if trend and seasonality is a component of the time series, but it's also going to be able to help us determine what order we're potentially going to need in terms of the seasonal decomposition. All right. Where am I? Mouse is there. So just a couple of notes here. More things that we've talked about already, but I just want to be able to formalize them here for you. So if a centered moving average smoother of order K is applied to a fixed period cycle data with fixed cycle length where K is the cycle length, then the smoother removes the cyclic component and reveals or estimates the trend. So that's exactly what we had in that last example here, which we knew exactly what that cycle repetition was. We knew it happened every 10 periods because we built it into the time series itself. So that is fixed in there. So when we did an order 10 smoother, it gave us a good estimate of what that line was. Now, it wasn't a perfect line when we added the noise in there because that noise is going to disrupt the smoother part of it because, again, there's those random fluctuations that are happening. But again, we get a good idea and we're able to estimate based upon this data what the trend is going to be. Now, another thing to note here. While a moving average smoother of order K applied to cyclic data with a fixed cycle length of K will remove the cyclic behavior and retain the trend for smoothers of orders greater than K or less than K. So what we're saying here is, again, in that example, the first thing that we started off with is an order 5. So it might be a multiple to get us up to 10, but here's the thing. It needs to be a multiple of 10 to be able to remove things perfectly. If I go a little bit under that, if I go a little bit over that, doesn't matter. There is still going to be, like I haven't been able to completely remove that cyclic component from it if I don't pick the perfect order. All right, I think the last thing for today is we're going to talk about decomposing a time series into its main component. So Today, we're really just focusing on understanding what's going on, and we'll talk about forecasting and being able to talk about the accuracy of the forecast in the next lesson. So we're starting with decomposition of seasonal data. So we define seasonal data in STAT 2601 as cyclic data that has fixed periods and has a pattern related to the calendar. So the same type of behavior happens month to month. So in this example here, we have monthly numbers of international air travelers. The data set not only has within year seasonal behavior, but also has a near linear increasing trend. So what we see, patterns happening here, this up and down, the wiggles as it goes. Now notice those wiggles get larger and larger and larger as we go, so the variance becomes larger and larger and larger. But we also see an upward trend in the data. So if this is the number of international air traffic travelers from 1950 up to, this is showing here in the graph, 1960 plus, what we're seeing is an increase overall in that. All right, in order for us to decompose our time series, we have to understand what the underlying model is. And there's two main ones that we deal with. We have an additive model and a multiplicative model. So with an additive model, think of it as we have our components. So we have, again, our trend, we have our seasonal, and we have our noise component. So I'm going to label our seasonal as S sub t, our trend as TR sub t, and the noise as Z sub t. So for an additive model, think of each one of those as vectors where they have their specific time components of that. We create a time series by taking the respective time components from each one of them and just adding them all together. So at time t, I'm taking, well, what is the seasonal component at that point? What is the trend component at that point? And what is the noise component at that point? And just adding them all together. Multiplicatively, this is different. Again, I have those same sort of vectors in here, but now I'm multiplying them all together. So it has a different impact than what it had beforehand. So we have a multiplicative change rather than an additive change. Now, how do we know which one we are in fact dealing with? It's really all about the squiggles in this case. So notice in my original graph here, my squiggles at the very, whoops. This did it the same thing in the last time around with this. Why is it doing this? I don't know. Where am I in my slides? Here we go. Don't know what's going on there. The same thing with recording last time. The PowerPoint just died out on me. Everything else is perfectly fine. That died out. My recording's still going, so that's good. All right, so I was saying, when can I tell whether I'm dealing with a multiplicative or additive? It's all about the squiggles. So if I notice here, let's see, where is my pen? Perfect. My squiggles in the original data start off relatively small, and as we get larger, the squiggles become bigger and bigger and bigger. So we think of this as it is, or the variance in this case is growing multiplicatively. The squiggles that are happening in the beginning versus the squiggles that are happening in the end, vastly different. Now it could start off big in the beginning, small in the end. This is leading us to believe that this is a multiplicative model. Whereas if we're looking at the squiggles along the whole time series and they're all acting relatively the same, then this is representative of an additive model. We can change a multiplicative model to an additive model simply by taking each one of the data points and using the log of that. So that's going to level out those fluctuations that we get, and a lot of times that's exactly what we do. We generate we transform the multiplicative data into additive data, mainly because a lot of times it's easier for us to be able to deal with. All right. So the general idea for decomposition, we can break this down into four main steps. Additive and multiplicative follow exactly the same interpretation, just how we do these steps are slightly different. I'm going to go through the steps piece by piece in terms of the additive. We're going to show a function that does this automatically for us. So we're not going to go through the multiplicative part of this, but if you understand the additive part, you'll understand the multiplicative part to this. All right, so step one is we want to estimate the trend component. We're going to be able to do this using a smoothing technique. All right, step 2 of this is we want to be able to remove the trend component, which results in a data set that is primarily made up of the seasonal fluctuations. Of course, there's still going to be that random component to it. From there, from that new data that we have, we're going to calculate an average. So if we understand that things are repeating itself over a period of time, we're just going to find, well, what is the averages over those periods of time? So I'm going to build a seasonal vector. I'm going to have a trend vector inside of there. And then if I remove both of those things from my original data, all that I'm left with is that noise. So that's how we decompose this. I find what is the trend, I remove the trend. I find what is the seasonality, I remove the seasonality. What I'm left with is just the noise. All right, so how do we do this in the additive process? So my additive process, this is my model. And I want to be able to predict, and this is where I have my hat. I want a estimate for what the seasonal component is, for what the trend component is, and what the random component is. So first thing I want to do, and I'm going to create vectors for this. I'm not looking for equations. I'm just looking for vectors. The first thing I want to do is create a vector that's going to represent my trend. And I'm going to do this using the ma.smooth.wge. So picking the right order of smoother is very key in first removing that trend component. So how do I remove the trend component? Well, if x sub t is my original data series, removing the estimate of what we just had, so simply just subtracting that off. So I have my original vector, I have my approximate trend vector, I subtract those two vectors. What I'm left with is my seasonal component and my random component. Now I want to be able to estimate what that seasonal component is going to be. How do I estimate what that seasonal component is going to be? Well, I'm going to organize the new data, this ST plus ZT, into, say, months, or again, whatever pattern or order we're in fact dealing with. And then what I'm going to do is, so let's suppose this is monthly. I'm going to organize my data into months. And if this is over a couple of years, I'm going to have, okay, well, this is my data for January of this year. This is my data for January of the next year, so on and so forth. So think of this as I'm building it like a matrix. Each column is going to represent a month. Each row is going to represent a year. And then all I'm doing is I'm going to take an average of each one of my columns. So I'm saying, what is the average seasonal impact on January? What is the average seasonal impact on February? What is the average seasonal impact on March? So on and so forth, all the way up to December. So I'm going to have an average for January all the way up to December. Now, if this repeats for a number of years, I'm just going to repeat that exact same average pattern over all of the years that I need to do it. And we'll go through an example of exactly what I mean by that in just a second. But that's it. I'm creating a new vector that's going to have this exactly the same repetition in pattern. And then I'm going to estimate what the error term is, or the randomness component, by simply just taking everything and just subtracting it all out. So I'm going to subtract out x sub t, which is the original time, or I'm going to take the original time series. Oops, this should be hat. I'm going to remove, there we go, the trend component. I'm going to remove the seasonal component that we just estimated, and what we're left with is just that random component to it. All right, so this is the graph that I want to get from being able to do this. So let's just jump into R for a second and show exactly how we come up with this. All right, so we're using the air passengers data. So I'm going to plot air passengers, which again is exactly what we saw here. This is a multiplicative model, so I want to be able to change this. So I'm just going to take the log of air passengers. And if I plot this again, notice those squiggles have flattened out, or leveled out in this case, where I can kind of bound them above and below by something. Okay. So the first thing that I want to do, and I know I'm dealing with yearly data here, and this is air traffic controller, so the pattern should happen every single year. The same repetition should happen every single year. And we can kind of look at just using the ACF log air. Same as before, very strong correlation at the beginning, so we're seeing a decrease. I'm seeing a bump back up, and around the 1 year, again, this is where it shifts back down. So I have that up and down sort of pattern here, so this is telling me I want a 1 year or 12-month cycle. All right, so I'm going to create a new vector. I'm going to call this log air.12, and I'm just using an MA smoother on it. And if I just smooth out my data and print it to the screen, gosh, I only really need the bottom because the top is going to behave in the same sort of way. So notice I don't have observations for each one of these, and that's simply because, again, there's some data points when I'm creating this new time series or this smooth time series that I'm not able to calculate. So I'm doing an order 12 even, so that's going to mean I take 1 point away. That leaves me with 11. Well, that's not an even number, so I remove one of those. It's down to 10. I can divide that by 2. So I'm going to have my middle point. I'm going to go 5 to the left, 5 to the right. That gives me 11 in total, but I want an order 12. So I'm going to go one more half, and there we go. So 6 points I need to my left, 6 points I need to my right. So notice here the last 6 points cannot be calculated because, again, I can't calculate this NA because I only have 5 points to my left. I need 6 to be able to do that. And the same is going to be true if I look at the top of this vector. All right, now I can create this into a time series. It's not a time series right now. All it is simply just a vector. So I can do log air. I'm going to call this SM12, so it's smooth order 12. I'm using the TS function. So this is the time series function. It creates a time series by, I'm inputting a vector here. So that's my log air.12. And I'm grabbing the smooth data from this. So I'm using the $smooth this in that specific frame. The starting time, 1949, first month, and its frequency is 12. And if I plot this, there we go. So I can clearly see that there's an increase. There is still some fluctuations that are happening inside of there, but that could just be the random noise that is happening. We didn't get a perfect line when we had the noise in here. We're still not getting a perfect line. That's perfectly fine. And again, I could print this to the screen. Now notice when I print this to the screen, this is slightly different now. What's different about this has the months in there. So it outputs it as a matrix where my columns represent my months, my years are represented by my rows. Otherwise, if I don't do this, and as I did beforehand, just take the smooth data, it just prints it as a giant vector. So here it recognizes that it is in fact a time series. All right. So what I'm going to do now is I'm going to take the original data, the log air passengers, and I'm going to remove the smoothed out data. So what this should leave me with is just the seasonal component left. No, sorry, the seasonal and the randomness of this. All right, so if I round this up, notice again, my output, what I have left here is just the seasonal and the noise. Now I've removed certain things, so I do have these NAs still inside of there. We'll have to deal with those. But look at the format of this right now. This is really the format that I want of this. Unfortunately, this is only outputting like this because it is a time series. What I need is, I need this data in a matrix form that is exactly like this, where my columns represent my months and my rows represent my years. So this is what I need to do. I need to be able to transform this data into this. Now, if I just plot this to give a quick look at this, this is my new seasonal data. Now notice it's not increasing, it's not decreasing, it's just flat along the way with these up and downs. That's because we removed the trend component to it. Now all of these up and downs are not perfectly of exactly the same size. That's the randomness that comes into this. Okay. So what I want to be able to do now is I want to build a matrix. So I'm going to take the original data and I'm just going to convert this into a vector. That's my line 77. Now I'm going to build a matrix. Now I'm specifically using the matrix function. I'm inputting that vector that I just created, which is my data in vector form. So removing the time series aspect of it. I'm saying the number of columns is 12. and I'm building this by row. Okay. So what this means is, because my data is laid out in months, I have two ways of building a matrix. I can build it starting with my columns, so I build it one column at a time, or I can build them my rows at a time. I want this built as rows because my first 12 observations represent 1 year. It should be on the same row. So that's exactly what we're doing here. So I'm saying the number of columns is 12, has to represent every single month, and I'm building this by row, so I'm setting by row is equal to true. So if I do this and I print this out now, okay, notice I have 12 rows. They're not labeled by months anymore because, again, that was just the output of the time series data. It was just still one vector, and I didn't want it that. I want it as a matrix. Here I have a matrix where I have 12 columns, and I have, in this case, 12 rows. Okay, now what I want to do is I want to be able to find what's the average per month. So I'm going to use, it's in matrix form, I'm going to use the call means function. So it's going to take the mean of each one of the columns. So I'm inputting the matrix that I want it to do. And now here's an important part, because some of those columns have NAs in them. Because I couldn't, or when we did that smoothing process, we're not generating a new time series with all of those same data points, because again, we can't. There was 6 points at the beginning that we could use and 6 at the end that we couldn't use. So here when I set na.rm equals to true, what it's going to do is it's going to look at each one of those columns, and it's not going to bother to calculate anything with an NA. So it's just going to skip right over that and go to the next data point in that column. If I don't put this in there, as soon as it sees an NA, it's going to break. And every single column has an NA in it, because the 6 original points and the 6 last points represent the first 6 months and the first last 6 months, or the first 6 months and the last 6 months. There we go. So every single month has an NA in it. So we want those removed. So removing that, look at my months. This is just a vector where the first entry is representing January, the last entry is representing December, and it's just the average. So it went down each one of those columns, which represented, again, that month over all of the years, and took the average of that. So the average for January is negative 0.8 or 0.8668069. You get the idea. Okay, this is a vector of size 12, but there's 12 years of data that we need. So what I'm going to do is I'm going to create a new vector based upon this vector of 12, and I'm just going to keep repeating this vector of 12 over and over again. So that same pattern is going to persist over and over again for 12 years. So I'm using the rep function. So I'm repeating these things. I'm repeating months, that 12 vector, and I'm doing it 12 times. So just pasting it one after another. So here's the first vector. Here's a copy of that. Here's a copy of that. Here's a copy of that. I'm doing that 12 times. And again, I want to turn this into a time series. And if I plot this, there we go. I have my up and down fluctuations, which is perfect the whole way through. So it's exactly the same year after year, because I've just taken that average and I repeated it over and over again. Okay, so I've got a seasonal vector of 12 years. I have a trend vector of 12 years where just the first 6 and the last 6 months aren't accounted for. Now I want to remove those from the original data, and all I'm going to have left is the noise. And that's the noise component to it. So if I plot this all together, I'm going to use the mfrow function, where it's just going to take in, or sorry, mfrow under the par function, which is just going to take a vector of how I basically want to be able to present this. I want a 2x2 grid. So I'm going to post these 4 photos next to each other in a 2x2 grid. So the first one starting at the top left will be air passengers, the original data. Moving to the right is going to be the trend. Underneath that, moving on to the next row, this is going to be the seasonal component, and last but not least, the noise component. And now I want to be able to turn this back into a 1x1 grid. There we go. So all of the information is there. Perfect. So it just plots those graphs. Now I can do all this very easily using the decompose function. So decompose, I'm putting that log air passengers data, and I'm just specifying the type. So it could be additive or multiplicative. This, because if it's an additive model, I use additive. And notice, again, if I plot this, it plots it all like this. It's exactly the same plot. I could replot this out in the same sort of way. Again, using the MF row 2x2 grid, plot my air passengers, the trend of that, the seasonal component, the random component, close that back up. We have basically exactly the same thing that we had beforehand. Perfect. So we can do that for additive, we can do that for multiplicative in just one command line. We don't have to go through the whole structure of all of this. I just wanted to show you this is exactly what we're doing. This is exactly what we get, and this is a faster way of being able to do that. Let's see, let's jump back over here. We're at that time, but I just have the quick last couple of slides here that I want to go through. So multiplicative, again, I'm not going to be talking about this. You can work through this one on your own. Instead of subtracting things out, we're either multiplying or we're dividing. That's it. It's just how we remove them is going to be different than how we did it additively. Subtraction happened beforehand, division is going to happen now, but exactly the same process overall. All right, so just a general idea. So imagine your sales spike every December due to holiday shopping. If you don't remove that predictable swing, you can't tell whether new pricing strategies actually boosted baseline demand or you're seeing just the December seasonality component to this. So many data sets that we find have already been seasonally adjusted. So seasonal adjustment or depersonalization is a statistical method for removing the seasonal component of a time series. It's usually done when wanting to analyze the trend and the cyclical deviation from that trend of a time series independently of the seasonal component. Now, the seasonally adjusted data allows for more meaningful comparisons of economic conditions from time period to time period. So what is good about this? Well, other than what I've kind of just said, trend clarity is the first thing that comes to mind. So seasonal adjustment removes the wave, the up and down sort of day-to-day fluctuations, so you see the true direction of your data. Are we actually going up? Are we actually going down? Or are we not? It allows for comparison. So in January this year versus anything, again, it kind of looks like that apples to apples comparison, because I've taken out those seasonal increases and decreases. So if I'm looking at January this year compared to anything else, again, if that seasonal component is taken away, I can actually tell what is happening here. And model needs, again, deseasonalization data is closer to stationary, so it improves the reliability of smoothing and forecasting algorithms, which we'll talk about in the next class. All right, so here we're basically just going to discuss the basic idea about seasonally adjusted data. Why is this? Of course, it had to crash again. Why would it not crash again? Just when we're at the very end, and it didn't even open. How rude. Okay, well, let's see here. Thanks for sticking with me, folks. Just give me 2 seconds to see exactly where I'm at. Here we go. They can never make this easy for me. All right, so how do we adjust the data, or the seasonally adjusted data? For us, super easy. We've already done this in the decomposition. We just take the original data, take the smooth or the seasonal data from it and just remove that, or the seasonal component from it and just remove that. So in the decompose, it breaks it down into its different components there, as you saw in the graphs that I've outlined. So you just take the one that has the seasonal component and you subtract it from that, and that's exactly what you get. So for exercise 3, oops, don't crash on me again, please. Exercise 3, that's exactly what we're going to do. We're going to do the seasonally adjusted data. And for multiplicative, we'll go back and do that in just a second. For multiplicative, I'm just dividing out instead of subtracting. So that's exercise 4 if you want to go through it. I haven't gone through that in the slide, so you can kind of skip over that part if you really want. But yeah. So just a couple of notes, and then I'm going to go back and I'll do that last one there. So in this section, we have shown how smoothing decomposition and seasonal adjustments are useful techniques to help analysts understand and visualize data. These techniques have been illustrated using various examples, things that we've simulated, some that we have not. For both additive and multiplicative, well, we haven't really done the multiplicative, but if you understand the additive, you've got the multiplicative side of this. And separation of the original time series data into its trend, seasonal, and residual, that's the noise component. In many cases, unless time series data sets is decomposed into its component parts, important information is hidden and unrecognized. So that's kind of a key thing as to, again, why we do these sort of things, why we strip these parts apart, or these components apart, so that we can actually see underlying what is happening with our data. Okay, so let's go back to our just one last time here. Well, not just one last time, but one last time for today. Exercise 3. Okay, so I'm going to create a log air passengers.adj for adjusted. So I'm taking my original data. Now, this is what I did here. So I took the decompose, used the decompose function, additive, and I stored this into log air underscore add. So I take this log air underscore add, $sign, so I'm going under the seasonal component of this, and I'm just subtracting that from the original data. And if I plot this, that's exactly what we have here. So we have the data that still has potentially cyclic aspects of this, so still up and downs that happen not in a 1 year period of time, and it still has trend and it still has noise. But what this again does is it allows us to see demand at different points in time without the influence of that seasonal component to it. So if things are, again, this is air traffic control, things around holidays, we're going to see major spikes. Non-holidays, we might see lulls at that point in time. So we'll see those up and downs, but now with that being removed, we can kind of get a better picture of what's happening from month to month overall, again, without that seasonal aspect added into it, or the overinflation of our data. All right, so that puts us at just over an hour and 10 minutes, so that's a good place to stop. So another lecture down. We'll get to forecasting the next time around, but that's a good introduction to time series to start. If you have any questions, comments, concerns, feel free to reach out. Otherwise, we will see you back here the next time. As soon as I can find my mouse to shut this off. Goodbye.